now here's what we're going to do next. You saw that for linear motion, forces caused acceleration. Okay. Now what you're going to learn is the parallel of force is torque, denoted by tau. The parallel of mass was moment of inertia, and the parallel of acceleration was alpha. So angular acceleration is caused by torque. Just by like linear acceleration was caused by force, angular acceleration is caused by torque. Okay. And so that's what we're going to learn. Okay. Now, so now here's the thing about torques. So how do you apply a torque? Well, you have to apply a force to an object. Now, the torque that this force causes depends on two things. It depends on how far from the axis of rotation you are, or about how far is the axis about which you're calculating. So let's say this object is fixed to rotate about that point. You apply a torque in this, you apply a force in this direction. The further this distance is, the greater the torque of this force. Okay, so this is called a moment arm. Yeah. And if you apply the same force over here, it'll cause a greater angular acceleration. Okay, so the efficacy of a force in causing rotational motion depends on its moment arm. This is the moment arm. Okay. Okay. What will this force do? It'll make it rotate counterclockwise. What will this force do? It'll make it rotate clockwise. So again, if a force makes it rotate counterclockwise, we take the torque positive, just convention. And if the force makes the object rotate clockwise, the torque is negative. Okay, so that's the convention. Now you can take the same force and shift it around, and if the force is pointing in this direction, so for instance, if force F1 was pointing like that, now you can see that the moment arm is that. Okay, well, let me do a better example. So, okay, so let's say instead we are taking the same force and applying it like this in this direction, and now the moment arm is only that distance. Okay, now the same magnitude force applied in this direction will cause a rotation angular acceleration that is smaller because the moment arm is smaller. Okay, so again, that is what we mean by the efficacy of force causing rotational motion depends on the moment arm. All right. Again, I urge you guys to go look at those applications, play around with those simulations. Okay. So what we're saying here is the product of force and moment arm is called torque. So the magnitude of the force times the moment arm is the torque. This force will make it rotate counterclockwise, which is positive. And again, you use your right hand, wrap your fingers in the direction of rotation, and your thumb points in the direction of the torque. Okay, wrap your fingers in the direction of the force, and your thumb points in the direction of the torque. Okay, so this is just to illustrate again. So here's the top view, there's the door, there's the hinge. Now you guys will understand why you put hinges on, the doorknobs on the end. So when you apply a force like this, you have the greatest moment arm. Okay, so this has the same moment arm as this, and since the magnitude of this force is greater than that, this will rotate faster. This will have a greater angular acceleration than this. Now, of course, if you apply a force like right there in the middle of the door, you'll have a harder time opening the door. This will have a smaller angular acceleration than this. And for some reason, if you apply a force like this, your moment arm is that, even though the magnitude of the force is the same, this will have a much smaller angular acceleration. It's much harder to open the door that way. Okay. Okay, so everything we said about the torque can be captured in this formula. Okay. And this formula says the torque, which is a vector, is R cross F. It's the cross product of R is R is the vector from the axis of rotation to the point of application of the force. So that's the vector R. And if you're applying a force like that, the force is that's the force. The torque is R cross F. And of course, you understand if the force is in the same direction as this, if R and F are parallel, R cross F will be 0. And so if you apply the force in this direction, this object will not rotate. So if you apply the force in the direction of the axis, okay. And again, so this formula captures everything. So torque is R cross F. Now in the next couple of slides, what we're doing is the following, and I won't go through the derivation. You saw that for linear motion, force was equal to mass times acceleration. Forces cause acceleration, and what we want is a similar formula for rotational motion, and that's what we're going to introduce. Okay, the parallel of force is torque, the parallel of mass is moment of inertia, and the parallel of acceleration is angular acceleration. Okay. Okay, so that's what this formula is telling you. The torque applied is moment of inertia times alpha, angular acceleration. And remember, so when was this formula valid? When, okay, so let's, when was this formula valid? Newton's second law was really force was equal to dP by dt, which is equal to d by dt of mass times velocity, d by dt from the chain rule times velocity plus m dv by dt, and dm by dt times v plus m times acceleration. So this formula was good as long as this term was 0. That is, the mass of the object was not changing. So similarly, this formula is good if di by dt is 0. That is, the moment of inertia of an object is not changing. Now, you guys have seen an ice skater that is spinning, and when she pulls her arms and legs in, she spins faster, and that's because her moment of inertia is changing. Di by dt is not 0. Okay, so this formula would not be valid then. All right. Anyway, so in this slide, what we're introducing is the parallel of this formula, which is this formula, and this formula is valid as long as moment of inertia does not change. Okay. All right. So there's the formula. So there's Newton's second law for rotational motion. Torque is I times alpha. So the net, so here's Newton's second law of motion for rotational motion. The net torque acting on an object is the moment of inertia of the object times alpha, the angular acceleration of the object. And again, this is good. And this works. This is for objects where the moment of inertia is not changing. An ice skater, like I said, when they pull their arms and legs in, their moment of inertia is changing. So this wouldn't be valid for them. Okay, so what this formula slide shows you is, now if you're pushing on an object and it has a velocity v, the rate at which you're doing work on this object, which is the power, the rate at which you're doing work is F dot V, and they're in the same direction as F times V. And so the corresponding formula for this is, for rotational motion is, so if this object is rotating and you're applying a torque by applying a force, the rate at which you're doing work the rate at which that force is doing work is tau times omega. Again, the parallel of F F got replaced, F gets replaced by torque, and velocity gets replaced by omega. And so the parallel of this formula is that formula. Okay. So the rate at which you're doing work when you're applying a torque to a rotating object is tau times omega. Okay, for linear motion, we had the work energy theorem. The net work done showed up as change in kinetic energy. For linear motion, you calculated kinetic energy like so. Okay, so the parallel for rotational motion is when you do work, that shows up as rotational kinetic energy. So final rotational kinetic energy minus initial rotational kinetic energy. And that's the work energy theorem. So exactly the same formula. Okay. And this slide summarizes everything that every equation that you saw for linear motion, there's the corresponding equation for angular motion. These equations are valid for a constant, linear acceleration constant, and the corresponding equations are valid for alpha constant. Okay, so this has some formulas that we haven't talked about. This is linear momentum, which is m times p, and we'll define angular momentum in one of the next chapters, L, which is I times omega. Okay, so anyway, here's Newton's second law. The net force is dp by dt, and the corresponding Newton's second law for rotational motion would be net torque is dl by dt, rate of change of angular momentum. Okay, so let me give you the recipe for getting angular formulas. So wherever you have x, replace that by theta. V by omega, A by alpha, oops, force by torque, mass by moment of inertia, linear momentum by angular momentum by omega, and so on. Or we'll say linear momentum by L. Okay. And so for every formula that you have for linear motion, by doing this replacement, you'll get the corresponding formula for rotational motion. Okay. And that's what this slide summarizes. So these are all the linear motion formulas that you studied in the first 9 chapters. And here are the corresponding formulas for rotational motion that you've studied in this chapter, and you'll study some of them in the next chapter. So, okay, here was the formula for work done by a variable force. And here's the work done by a variable torque, and that will depend on theta. Okay, so that finishes this chapter. I'll stop the recording, and